Hello, Professor. We could start.
Okay, so thank you. Let's start today's lecture. Let me start by recalling you the definition of the class of spherical homogeneous spaces given by several equivalent properties. We have seen them and proved their equivalence on the previous lecture, and here is the list of them, which I recall. So the first one is about existence of an open orbit for a Borel subgroup on a given homogeneous space Y. The next two properties are just reformulations of the first one in terms of Lie algebras. And the fourth property is still a reformulation of the first one, now in terms of invariant functions, Borel invariant functions. This is in view of Rosen-Licht theorem, which says roughly that general orbits are separated by invariant rational functions. So if there are no invariant rational functions, this means that there is an open orbit. And if there are non-constant invariant rational functions, then this means that general orbits are separated by them and form an infinite family. Okay. So the next four properties are about are versions of the multiplicity-free condition. That is, the representation of G in sections of any line bundle over my homogeneous space should be multiplicity-free. Each irreducible submodel should occur at most once in the decomposition of this representation space. The condition 6 is just reformulation in terms of semi-invariant vectors in irreducible representations of G. This is in view of Frobenius reciprocity. And the conditions 7 and 8 are reformulations of particular cases of the conditions 5 and 6 respectively, in the quasi-affine case in which it suffices to consider only the trivial line bundle over Y, whose space of sections is just the algebra of regular functions over Y. So this is the definition which I recalled for you. And now let me turn to examples of spherical homogeneous spaces. So examples. The first example actually explains the name spherical. The first example of a spherical homogeneous space is just a sphere, say of dimension n-1, which can be defined as the set of points or vectors in an n-dimensional vector space, or affine space if you like, this doesn't matter. Satisfying a quadratic equation, say in the standard form, x1 plus etc. plus xn squared equals to 1. It is a homogeneous space under the group SON, which preserves this quadratic form, and the stabilizer of a point is isomorphic to a smaller group SON-1. So let's check that the sphere given by this equation is spherical in our sense, in the sense of the definition which I gave on the previous lecture and which was on the previous slide. So let's change coordinates in the vector space k to the n. So that the group SON will preserve a quadratic form given by not this equation, the standard one. But we change the coordinate in such a, the coordinates in such a way that the quadratic form will have a matrix with matrix, which is not the unity matrix as here, but a matrix denoted by Q with units on the secondary diagonal, like this. It is again a symmetric matrix of full rank, and since all quadratic forms, all non-degenerate quadratic forms are equivalent over an algebraically closed field, we can change coordinate in such a way that the quadratic form preserved by my group will have the following matrix. Then the group SON is given by the equations. So let me write down the equations for the group G, which is SON in my example. G small times Q times G small transpose equals Q. This, and also since I consider the special orthogonal group, there is yet another equation, the determinant of G equals 1. These are the equations for the orthogonal group, for the special orthogonal group, preserving the quadratic form with this matrix. The Lie algebra, if we differentiate these equations in G, in small g at unity, we'll get the linear equations for the Lie algebra of the group SON. So the Lie algebra, which I write like this in German letters, is given by the following equations: Xi times Q plus Q times Xi transpose equals to 0. This is the differential of the equation on the left of the first equation. And if we differentiate the equations on the right, then we get just the equation that trace of Xi should be equal to 0. Xi is the tangent vector, of course. So the first equation can be rewritten in the following form: Xi equals to minus Q inverse times Xi transpose times Q. But Q is self-inverse, so I may not write here Q inverse, just write Q times Xi transpose times Q. This is another form of the first matrix equation, and actually this equation defines the class of skew-symmetric matrices, which are skew-symmetric with respect to the secondary diagonal. Skew-symmetric matrices with respect to the secondary diagonal. Well, if you like, I can draw it like this. So these are the matrices of the form 3, 4, 5. Okay. So the matrices should be skew symmetric. Which means that when we reflect with respect to the secondary diagonal, we change the sign. So if we had sign plus here, we get sign minus here, something like this. Okay, this is the schematic schematic picture for this equation. And also we see that skew-symmetric matrices have automatically trace zero. So this second equation is actually redundant. We can remove it. Okay. What is the advantage of this choice of coordinates in which the quadratic form preserved by SON has this matrix? The advantage is that important subgroups in G and the Lie algebras can be represented nicely in the matrix form. In particular, in these coordinates, we have the Borel subgroup, or maybe better to say the Lie algebra of the Borel subgroup, the Borel subalgebra, is given by matrices of the following shape. So matrices, matrices which are both triangular and skew-symmetric. So we have zeros here, and we have something on the diagonal and above, and so that this triangular piece on the diagonal and above is skew-symmetric with respect to the secondary diagonal as above. This is the matrix form of the Borel subalgebra in this case. And the stabilizer of a point on a sphere, the subgroup H in my general notation, H. For the stabilizer, for H, I can take the stabilizer of any non-isotropic vector in my vector space K to the n. If I take a vector with inner square 1, then it will belong to this sphere. But I can take any non-isotropic vector because up to a multiple we can take it to this sphere. We can multiply it by a factor, by a scalar factor, and obtain that the quadratic form will take value 1 on this vector. So let me take the vector which is the sum of the first and the last basis vectors in the standard basis, E1 and e to the 1 and e to the n. Okay. So I mean again that so let me remove these drops of ink to make, to make the formula looking better. Okay, so this vector E1 to plus En, E sub 1 plus E sub n, has inner square 2. So the value of the quadratic form on this vector is 2. If we divide it by the square root of 2, then we get a vector on S to the n minus 1 on this sphere, and this is the stabilizer. So my homogeneous space is G mod H. Of course, this subgroup is isomorphic to SO n minus 1. And what is the Lie algebra of H in the matrix form? So the Lie algebra of H consists of those matrices in the Lie algebra of G which annihilate the vector E1 plus En. This is the equation. And now what is it in the matrix form? Let's take a look. What is this Lie algebra in the matrix form? Let me try again to draw a picture for you. Excuse me. Like this. Okay. So let me distinguish the first and the last column. Sorry. The first and the last column. And also the first and the last row of this matrix. Like this. So the matrix should be skew symmetric with respect to the secondary diagonal. In particular, this means that here, excuse me, here and here we should have zeros. And also, since this matrix should annihilate the vector E1 plus En, the sum of the first and last column should be 0. So the sum, yes, the sum of the first and the last column should be 0. So these two columns of the matrix should be mutually opposite. This means in particular that we have 0 here and also 0 here. And if we have a column vector of the size n minus 2 here, say v, then here we should have minus v. Here we should have v transpose. Here we should have minus v transpose. And in this middle block of size n minus 2 by n minus 2, we should have something which is skew symmetric with respect to its secondary diagonal. So if we have something here, then on the symmetric place matrix entry, we have the same thing with the opposite sign. So this is the matrix picture for the Lie algebra of H. And now if you compare this with the description, with the matrix description of the Lie algebra of B, of the Borel subgroup, you easily see that if you take, so this implies that if you take arbitrary skew symmetric upper triangular matrices of this form, and you add arbitrary matrices in H of this form, then you get arbitrary skew symmetric matrices with respect to the secondary diagonal of this form. So we get the condition 2, I guess. Right? Yes, we get the condition 2, that the sum of the Borel subalgebra and the Lie algebra of the stabilizer, maybe conjugate one of another point, equals to the Lie algebra of G. Or the condition 3, which is the same thing. So we have checked that the sphere, the usual sphere, is a spherical homogeneous space. And this explains the name. By the way, let me say a few words about names.
Hey, Professor.
Yes, please.
So in characteristic not zero, we have problems, right?
Well, in characteristic non-zero, the statement is true, but in characteristic non-zero, we have to argue a bit differently. By the way, if you in this example, if you take characteristic, any characteristic other than 2, then this argument has no problem.
The same statement works for characteristic not other than 2. I just wondering how it goes when characteristic is 2.
Well, in characteristic 2, you have to argue differently. You cannot use Lie algebras in this way because of because the orbit map is non-separable in this case. So I don't want to wander in positive characteristic, by the way, because my assumption is that characteristic is 0. But just let me say that there is a group argument. There is an argument on the group level, which can explain that the sphere is still spherical, even in characteristic 2. Okay. But let me stick to characteristic 0. I don't want too many complications. Okay. So let me say a few words about names. So the name spherical subspherical homogeneous space I guess it can be traced back to a paper of Brion, Luna, and Wust. Brion, Luna, and Wust of 1986, in which this name appeared, I guess, first, at least in the algebraic setting. This is for sure. The name spherical subgroup this is the name for the subgroup H, a stabilizer, the stabilizer of a point in a spherical homogeneous space, goes back to Manfred Kramer. This is 1979, I guess. Well, he considered Lie theoretic setting, not algebraic setting, but Lie theoretic setting. He considered compact Lie groups and compact subgroups in compact Lie groups. But his definition was very close to ours. But of course, the notion itself appeared much earlier. So this is only about names. For instance, this last 4 conditions about multiplicity-free property, it was proved that these conditions are equivalent to sphericality. It was proved that these maybe last 2 conditions, not last 2, the conditions 5 and 6, and in the quasi-affine case, they are equivalent to the conditions 7 and 8. So these multiplicity-free conditions, that they are equivalent to existence of an open Borel orbit. This was proved already. So let me write down like this. So the multiplicity-free property, multiplicity-free condition, and its equivalence with the other conditions defining sphericality. This goes back already to Weinberg and Kimmelfeld. Of 1978. Though they didn't use the name spherical, they didn't speak about spherical homogeneous spaces, but essentially they proved that conditions from 5 to 8 are equivalent to conditions from 1 to 4. Okay, so this is about names. And let me give you more examples. So my second example is flag varieties, or better to say generalized flag varieties. Flag varieties. A flag variety or generalized flag variety is by definition the quotient space of G modulo a Borel subgroup. So it is immediate to check the multiplicity-free property. that is the condition 5. This one, that the representation of G in space of sections, in the space of sections of any line bundle over a generalized flag variety is multiplicity free. Why so? Because we know by the Borel-Well theorem that actually this multiplicity, this space is either zero or carries on an irreducible representation. So the multiplicity free property follows from the Borel-Well theorem. But also we can check the existence of an open Borel orbit. To explain this and for other purposes, we have to recall more about the structure of reductive groups and their Lie algebras. So let me make a digression. Well, maybe you know this well, you should know this at least to a certain extent, but anyway, let me make a digression. Recall you what is a root decomposition. Of the Lie algebra of a reductive group. So consider the adjoint action of the maximal, of the chosen maximal torus, say T, on the Lie algebra of G, of my reductive group G, the adjoint action, the action by conjugation. This is a linear representation, and it is well known in the theory of algebraic groups that all linear representations of algebraic tori are diagonalizable. In particular, this adjoint representation is also diagonalizable.
Well, does the diagonalization property does not depend on the choice of the maximal torus?
Yes, exactly. This doesn't depend on the choice of the maximal torus. We just choose one, or all maximal tori are conjugate, so it doesn't matter which torus to choose. They are, in a sense, one, and they look.
Oh, I forgot that they are conjugate. Sorry.
Okay. So this representation is diagonalizable, and this means that the Lie algebra of G, can be decomposed as the direct sum of eigenspaces for this T action. The eigenspace of weight 0 is just the Lie algebra of T. And the eigenspaces of non-zero weights, let me denote them by G sub alpha. Alpha is the eigenweight. So these eigenspaces are called root subspaces. And their eigenweights, alpha, these alpha are called roots. They run over a finite set of characters of T.
What
denoted? Yes?
The decomposition, the first part of this decomposition is what?
The first part of this decomposition, the first summon, is the Lie algebra of T. This is small t in German letters. This is small German t, the Lie algebra of T. Okay?
I see.
Which is also known as the Cartan subalgebra. Another name for this maximal toral subalgebra or the Cartan subalgebra. Okay, so this set of weights called roots is a finite set. So this delta is a finite set of non-zero characters of T. And this set is called the root system. Let me draw a picture for you again. So it looks like this. So we have, say, let me start here. Excuse me. Choose another color. Okay.
Well, Professor, I want to ask a question.
Yes, please go ahead.
How can we conclude that different characters correspond to different eigenvalues?
Well, characters are just eigenvalues. I'm not sure I understand well your question. Characters are eigenvalues for the action of t. So each of these alphas is a character of t. And when a big T, when the group T acts on this root subspace, it just multiplies the vectors from this subspace.
Yes, I know the characters are eigenvalues. I mean,
yes,
the subspace, the eigenspace subspace is not always one-dimensional, right?
I didn't say anything about the dimension. I will say about it in a minute. Okay, so I just didn't finish. Let me just draw a picture of how the root system looks like. And then we'll say more about root subspaces. So this is a picture. Let me just drop here. So these are roots. Roots. They have different directions. I will say more about the directions in a minute. So this is a root system, okay? And as for the root subspaces, this was a good question about root subspaces. So all root subspaces are one-dimensional, actually. Each of the root subspaces is spanned by a single vector. They are called root vectors, non-zero vectors. Let me denote any root vector generating the respective root subspace by E sub alpha. Okay. So let me write down what does it mean that it is a root vector. I already said this in words, but let me write down the formula. So if you apply the adjoint action of some element t in big T to the root vector, then it is just multiplied by the value of the character alpha. At t, I use the exponential notation for the values of characters on elements of my torus in view of the additive notation for characters. So when you multiply the characters, actually these exponentials sum up, they add one to another. Okay, so this is the formula saying that this E alpha is indeed an eigenvector. Okay. And what can be said else about this root decomposition? So this root system, the set of roots, this set delta, is highly symmetric. In particular, this means that if you choose a hyperplane, let me write down this hyperplane. If you choose a hyperplane in the space, in the vector space generated by characters, a hyperplane, say, script H. So choose hyperplane script H in the vector space, say, of rational numbers generated by the character lattice, which does not intersect, which does not contain roots. So H intersect with roots is empty. So choose such a hyperplane, and then the whole set of roots is subdivided in two parts. The hyperplane H subdivides the vector space in two half spaces, and we can subdivide the set of roots in two parts, delta plus and delta minus. So delta plus is the set of roots sitting in one of these half spaces, and delta minus is the set of roots sitting in the opposite half space. And the property of the root system is that the root system is symmetric with respect to 0, which means in particular that delta minus equals to minus delta plus. These two halves of the root system are mutually opposite to each other. Then we can say so what is the relation with the structure of the reductive group G and its Lie algebra? The Lie algebra of the Borel subgroup B, actually containing T, actually equals the direct sum of the Cartan subalgebra, this Lie algebra of the torus, and the sum together with the sum of all root subspaces corresponding to this set delta plus, the set of positive roots, with respect to some hyperplane, to some subdivision of the root system corresponding to some hyperplane H as above, as before. So for some H. Okay, we can choose H in such a way that my Borel subalgebra is given by this formula. By the way, if we take only the sum of the root subspaces, then we get the Lie algebra of the maximal unipotent subgroup, which I denoted by U previously. And this is the Lie algebra of U. What we can also see from this decomposition, it is that we may consider another Borel subgroup, which is called the opposite one to B. So opposite.
So the hyperplane is chosen. Yes. Is chosen that the set delta is symmetric with respect to H, right?
The hyperplane H can be chosen so that the Borel subalgebra is the sum of T of the Cartan subalgebra and those root subspaces which correspond to the roots from delta plus, from this upper half space.
So H is chosen that so that the delta is symmetric with respect to H, right?
Well, delta is just symmetric with respect to 0. So for any root, the opposite vector is also a root. This condition doesn't depend on H. It just says that if you have a root, say this vector is a root, then the opposite vector is also a root. And this automatically implies this equality for any H satisfying this condition. If delta is symmetric with respect to 0, it is symmetric. No. I mean, it is, well, it is not symmetric with respect to the hyperplane H. No. When you reflect along the hyperplane, you may go out of the root system. It is not true that that delta is symmetric with respect to the hyperplane H. It is symmetric with respect to 0, and this means that any hyperplane of this form, containing no roots, subdivides the root system in two mutually opposite halves, in two mutually opposite parts. Okay.
Oh, and we use that the character and its inverse correspond to the same eigenspace, right?
No, of course they correspond to different eigenspaces because these are different characters. alpha and alpha inverse or minus alpha in the additive notation, these are different characters of T, and they correspond to different eigenspaces, to different root subspaces.
Oh, so the theorem of decomposition, the decomposition of B, not the decomposition of G. Oh, I see.
So in the decomposition of G, you take all roots, and in the decomposition of B, you take only half of the root system, only positive roots, okay? This is a smaller sum than this one. This sum is 1/2 of this sum, okay?
Okay, I know, thanks.
Okay, so let's go ahead. Then the opposite Borel subgroup or Borel subalgebra, opposite Borel subgroup or subalgebra is given by the following formula. So let me define the opposite Borel subalgebra, because for subgroup it is just the algebraic subgroup with this subalgebra. So B minus is the sum of the Cartan subalgebra and those root subspaces which belong to the other half of the root system, corresponding to negative roots, to roots in delta minus. So this is the opposite Borel subalgebra, and again the sum of root subspaces, of the root subspaces corresponding to the negative roots, correspond to the maximal unipotent subalgebra, maximal nilpotent subalgebra, you can call it like this, denoted by delta minus in this B minus. As for the respective Borel subgroup, big B minus, it has the following property. Its intersection with B equals to T. It is visible on the level of the Lie algebras. If you intersect this Lie algebra with this one, you get just the Lie algebra of T. But also it is true on the group level. So this is what I wanted to say about the root decomposition. And what is the outcome from this root decomposition for our example, for the example of flag varieties? So let me turn to the next page. We get then that.
Hey, Professor, I want to ask a question. Sorry.
Okay.
How do we choose delta plus? Well, either side could be delta plus.
So we choose delta plus. We choose delta plus as the set of vectors, the set of roots, lying in one of the half spaces with respect to this H.
So either side can be delta plus, right?
Yes, of course.
So this the opposite Borel subgroup is a Borel subgroup.
The opposite Borel subgroup corresponds to delta minus.
So it is a true Borel subgroup, but is not the origin Borel
yes,
subgroup.
Of course, it is another one. There are many Borel subgroups and many Borel subalgebras. They are all conjugate, but there are plenty of them. Okay. So B plus and B minus are different. They are they intersect only in T. Okay. Okay. Then it is clear from what we have explained before that the sum of the opposite Borel subalgebra and the Borel subalgebra, the initial one, it just equals to G. And this implies that the product of the Borel subgroup B minus with B is an open subset in the group G. It is called a big cell in G. Big cell. And this implies that the orbit of B minus under B minus of the base point in the flag variety, so X is the base point in the flag variety, which is my Y, my homogeneous space Y. The openness of this product B minus times B in G implies that the B minus orbit of this point X is open in Y. So we get the first condition defining the spherical homogeneous spaces. Okay. By the way, in our basic example, in which G is GLN, and for T we can take the diagonal torus. Let me draw it better with this line tool. The diagonal torus what are the root subspaces? What are the root vectors? So here, for the root vectors, we can take just matrix units, E sub ij. This is a matrix which has, again, let me use this drawing tool. This is a matrix which has a unit on some place. Say on the entry AJ. Excuse me. A matrix which has a unit on the ith row and jth column, and zeros on other entries. So these matrices are root vectors. The respective roots alpha are just epsilon I minus epsilon j. Well, let me recall that epsilon I is the character of this torus T, which takes a diagonal matrix to its ith matrix entry on the diagonal. So these are the weights, the eigenweights for these matrices, and the root set is the set of all this. So I different from J. The set of roots is the set of all such characters, epsilon I minus epsilon j. The set of positive roots, so alpha is a positive root, delta plus, if and only if I is less than j. So this hyperplane h, script h, can be chosen in such a way that the set of positive roots is given by this inequality. The Borel subgroup is what we already know. It is a group consisting of upper triangular matrices. Upper triangular matrices. It is indeed the sum of diagonal matrices of the Lie algebra. Well, if you speak about the Lie algebra of B, it is the sum of the Lie algebra of diagonal matrices, and all these root subspaces spanned by root vectors corresponding to the positive roots with I less than j. This means that the respective unity element is above the diagonal. The opposite Borel subgroup is, of course, the set of lower triangular matrices. Lower triangular matrices. So we have zeros here and something on the diagonal and below. And the big cell in this case consists of the matrices in GLN. Let me again draw this picture. Like this. So you may consider the upper left corner minors of such a matrix, the element in the upper left corner, then the 2 by 2 minor, and so on. And the condition that the element belongs to the big cell is that each of these minors, say this is delta sub I, where I is the size of this block. So the condition is that all these minors should be non-zero. So this is the condition for a matrix in GLN to belong to the big cell, to this product of B minus and B. So this B minus lower triangular matrix with upper triangular matrix, non-degenerate. So a matrix. Yes?
What is delta I? The
delta I is the determinant of this submatrix, the determinant of this block. Okay.
Or the principal, the
principal minor, the principal corner minor. Yes, like this. It is a determinant of this I by I block. Okay. So it is an exercise for you to check that. Let me write down like exercise. Exercise 1 for you to check that these conditions are equivalent to saying that a matrix is a product of a lower triangular non-degenerate matrix and an upper triangular degenerate matrix, non-degenerate matrix.
Hey, Professor, we only need the order, the principal minors, right? Not all principal minors.
or to belong to the big cell.
We only need n principal minors. Oh yes.
Yes. The upper left corner minors. The minors sitting in the left corner of the matrix. Okay, let me stop. I'm sorry for taking 5 minutes from the break, but let me stop here. Let me stop the first half of my lecture here. If you have any questions, then please ask. Now we still have a 10 minutes break, shifted by 5 minutes, but please ask your questions if you have any.
Hey, Professor.
Yes?
Could you list all the exercises in a single file so that we can we can easily check what exercise we have done and what exercise we will do.
Well, you asked me to list all exercises. Actually, the exercises are in the notes, in the PDF notes,
yes,
which you have.
But it like this, the exercise is not explicitly write down or what should we solve. So if we check exercise like from some time after the course, we may not understand what the exercise.
Well, so what is your suggestion? To write more explicitly in the notes? What are the exercises?
Well,
I just don't understand your suggestion. What do you...
Send a PDF file to Wuhan, maybe.
So this is a suggestion to Wuhan. Okay, so but anyway, I formulate each exercise explicitly during the lecture. So if you are not sure about the formulation of some exercise, you can turn on the video and listen to my formulation. Then I guess that everything which is unclear will become clear after you check the video record. But I also hope that most of the formulations are explicit in the notes. Maybe for this exercise, so it is not quite explicitly written. So the exercise here is to check that an element, a matrix, n by n matrix, belongs to the big cell of GLN, so belongs to this product, if and only if all upper left corner minors are non-zero. This is just a short formulation for the notes, but orally I formulated it in expanded way, so I hope the formulation is clear. Okay. Any more questions?
Yes. I want to ask some strange question.
Please go ahead.
You check that the general fact varieties and the sphere are both spherical varieties.
Exactly.
And I want to know that is there well, I think my question involves some non-algebraic closed field, so it may not be suitable. So I only will ask. So I will only ask part of the question. Is there some homogeneous space which is a Lie quotient that is not spherical?
Well, there are plenty of them which are not spherical. Actually, for instance, if you look at the first condition defining sphericality, then you see that the requirement is, well, maybe it's better to look at the second condition or third condition. The requirement is that the sum of the Lie algebra of the stabilizer and some Borel subalgebra equals to the Lie algebra of the whole G. In particular, this means that the dimension of the homogeneous space Y, which is G mod H, is not bigger than the dimension of the Borel subalgebra or subgroup. So the dimension of Y should be less or equal than the dimension of B. And this is a strong restriction. This means that the spherical homogeneous space cannot be too big. And the stabilizer, on the contrary, the stabilizer cannot be too small. It has a dimension bound, a dimension restriction. So you can imagine plenty of homogeneous spaces which are not spherical. Actually, most of them are not spherical. Sphericality is a nice distinguished property. Is it clear?
Yes. I still have a not so mathematic question. Since the definition of spherical involves the maximal solvable group B to have an open orbit, which means that the space Y is close to some homogeneous quotient of B, close. So why don't we call this space solvable varieties?
Well, I don't know. Well, this is a terminological question. I don't know. Actually, I explained why the name spherical is used, because it comes of spheres, spherical functions. So basically from harmonic analysis, from representation theory, because of this multiplicity-free property. Maybe you know what are spherical functions in harmonic analysis. So they are related to the multiplicity-free property for the action of...
comes from harmonic analysis. Oh, I see.
Yes, yes. Why not solvable? Well, so I guess that if the founders of this theory, if this idea could come up to the mind of the founders of this theory, then maybe the name would be different. But it is already a history. We cannot change the name after 30 years of development of the theory. So maybe it is a reasonable question. Why not consider varieties which carry on only an action of a solvable group with open orbit? So why do we need the action of the big group G? This is again because of representation theory, and actually I hope that in my further lectures you will see that the action of G is indeed important to get a nice theory. So the requirement, this requirement 1, the condition 1, is about the action of B, but it is important to have the action of a bigger reductive group G to create, to construct a nice theory for such kind of homogeneous spaces.
Okay, thanks.
Well, okay. Well, according to my watch, 10 minutes already passed, so we can continue the lecture. Let me turn to the last page. So we are working on examples of spherical homogeneous spaces. So we have seen the sphere, generalized flag varieties, and also, of course, partial flag varieties give you another bunch of examples. The third example, the third class of examples is partial flag varieties. Partial flag varieties, which are G over P, where P is a parabolic subgroup containing B. Why it is a spherical variety? Well, because we have a projection map, a surjective projection map from G mod B to G mod P, we already know that G mod B is a spherical variety. It contains an open barrel orbit. And the image of this orbit in Y is, of course, an open barrel orbit in the partial flat variety. Okay? So partial flat varieties are also spherical, and as particular cases, you immediately see that the projective space P to the n is spherical. So here G is GL n plus 1, and P is a parabolic subgroup which stabilizes, say, the point corresponding to the first basis vector in the respective vector space. So it is a subgroup of matrices of this form. Let me write again a matrix for you like this. So you have something in here. You have zeros in the first column, except for the upper element. And you have something in here. This is a parabolic subgroup, which is a stabilizer of a point in the projective space. And a more general example is Grassmannians. Grassmannian of m-dimensional subspaces in a vector space of dimension n. So here G is GLN, and P is again a parabolic subgroup of the similar form. Like this. So there are blocks. Maybe let me make this block a bit bigger. There are blocks with zeros here and anything here. And the size of this block is, well, let me write the size here. So it is m by m. The size of the upper left block is m by m. So this is the stabilizer of a point in the Grassmannian of m-dimensional subspace. So Grassmannians, all Grassmannians are spherical homogeneous spaces because they are particular cases of partial flat varieties. Yet another example, so example 4, is the variety of smooth quadrics in a projective space. So let me denote this variety as Q sub n. The variety of smooth quadric hypersurfaces in an n-dimensional projective space. It is a homogeneous space under the action of the group PGLN plus 1, the group of automorphisms of this projective space, And the stabilizer of a given smooth quadric is the projective orthogonal group, corresponding to the quadratic form in homogeneous in projective coordinates defining this quadric. We can take the base point to be the following quadric. Let me denote it as Q sub 0. The base point is the quadric defined by.
I think this space does not only include smooth quadric.
Well, this is my notation for the space of smooth quadric hypersurfaces. I just use this notation. So in my notation, it includes only smooth quadrics.
Well, I think non-smooth ones included in the quotient.
No. I mean, all smooth quadrics are equivalent with respect to the action of this group PGLN plus 1, because all non-degenerate quadratic forms in n plus 1 variables.
Yes.
Okay, and this is just the stabilizer. So only smooth quadrics are here. Okay, and for the base point, we take a quadric given by this equation, x naught square plus etc. plus xn square equals to 0. This is an equation for the smooth for a smooth projective quadric. And this is our base point given by the standard quadratic form, a non-degenerate quadratic form in n plus 1 variables. So I want to explain why this homogeneous space is spherical. Basically, this follows from the Gram-Schmidt orthogonalization process. Gram-Schmidt orthogonalization. What does the Gram-Schmidt orthogonalization process say? It says basically that if you are given a quadric in this space Q sub n, which is defined by a quadratic form, by a quadratic equation, so like this, sum of Q sub ij xi xj equal to 0 over all I and j. If you are given such a smooth quadric defined by this non-degenerate quadratic form, and if all upper left corner minors of the matrix of this quadratic form are non-zero, so if all these determinants of the matrices of Qij, where I and j run over the range from 1 to k, if all these determinants are non-zero for any k, from, I would say, 0 to the n, then there exists a triangular linear substitution of variables. There exists yes.
Sorry, so the ij is from 1 to k.
Excuse me, I'm sorry. Yes, this is a typo. Let me.
But your k is from 0 to n.
Let me put from 0 to k here. Okay. Now it is correct. So thank you. So if this condition about non-vanishing of all upper left corner minors is satisfied, then the Gram-Schmidt orthogonalization says that there exists a triangular linear substitution of variables taking this quadratic form to this standard shape, x naught square plus etc. plus xn square. In geometric terms, this means that there exists an element in the Borel subgroup which consists of upper triangular matrices we can take this for a Borel subgroup. There exists an element from the Borel subgroup which takes this point Q to the base point Q naught. This is just the geometric formulation of Gram-Schmidt orthogonalization process. And this implies, of course, that the Borel orbit of the base point Q naught is open in the space of smooth quadrics, because it is just defined by these inequalities. It consists of all quadrics whose matrix of a quadratic form defining this quadric has non-vanishing upper left corner minors. These are inequalities defining the open Borel orbit. So the space of smooth quadric hypersurfaces is again spherical. And maybe the last example, example 5, will be the group G itself. So G is my connected reductive group. Let us take for the homogeneous space the group G itself. But now we consider G as a homogeneous space for the bigger group, for the doubled group, G cross G, which acts on G in a natural way, so that the left factor acts by multiplication on the left, and the right factor acts by multiplication on the right. Left and right multiplication. Under the action of this bigger group, G cross G, the group G itself is a homogeneous space. And the stabilizer of the base point, for which we can take the unity element of G, is just the diagonal G. G itself embedded diagonally in the direct product. So why this homogeneous space is spherical? It's very easy to explain. Because for a Borel subgroup in G cross G, we can take the product of B minus and B. B minus cross B is a Borel subgroup in G cross G. And if we take the orbit of the base point, which is the unity element, under this Borel subgroup, we get just the product B minus times B, the product in G. It is a big cell, and we already know that it is open in G. So we get the first condition, openness of a Borel orbit, existence of an open Borel orbit. And this shows us that this homogeneous space is also spherical. So let me finish this, conclude this list of examples by a series of exercises for you. So the first exercise, the second one, the first we have already seen the first one. The second exercise. Which of the following homogeneous spaces are spherical? Which of the following homogeneous spaces are spherical? So the first one is GL2 3 times over the diagonal GL2. The second is the same for GL3. Excuse me, by the way, in the previous line, I put GL3. at one place, and here it should be GL2. So GL2 3 times modulo diagonal GL2, GL3 3 times modulo diagonal GL3, and also GL2 4 times. Modulo the diagonal GL2. Which of these homogeneous spaces are spherical? This is the second exercise. The third exercise.
I have a question.
Please.
In your example 5, just above this, in this slide, and should
Yes.
right multiplication or left, one of them should be composed with inverse.
Sure.
That...
Yes, sure. I just skipped these technical details. When you multiply from the right, you have to compose with the inverse, because otherwise you do not get an action in the usual sense. You get the anti-action. But if you want to get an action with the usual axioms, then you have to compose with the inverse. You are right. Thank you.
Sorry.
Yes.
So what's the action in the 3 examples in your exercise?
What is the action? Well, these are just homogeneous spaces. These are the spaces of the form G
so
over H. So Gx.
As cosides.
Say it again. What is your question?
So as a coside or something else.
Coside. Yes. It is the space of cosides. You may consider these homogeneous spaces as spaces of cosets, left cosets. Okay, so Gx on the left. Okay. Well, the third exercise is the following one. Yes.
About the third question, it's the third example in exercise 2. Shouldn't it be diagonal GL4 or GL2 or the product?
No, GL2. 4 copies of GL2 modulo diagonal GL2. This is my example. The question is whether it is spherical or not. Okay?
Okay, thanks.
Okay, so the third exercise is as follows. So suppose we have a connected reductive subgroup H in a connected reductive group G. So G is always a connected reductive group in my notation, but suppose H is a connected reductive subgroup. Prove the following. The homogeneous space G cross H modulo the diagonal of H. So it is clear that since H is a subgroup in G, it can be embedded diagonally in G cross H. Okay? So we may form this homogeneous space G cross H modulo diagonally embedded H. So prove that this homogeneous space is spherical if and only if the following property holds. For any irreducible representation of G in some vector space V, its restriction to H, it is no longer irreducible in general, but it is multiplicity free. That is, if you decompose the restriction of this G module to H, then you get a sum of irreducible H modules, each one occurring only once in the decomposition. So the multiplicity-free property for any restriction of an irreducible representation of G to H. Let me denote this property in some way, like this, M, F, R. So this stands for multiplicity-free restriction. Okay, and
So,
yes.
in the definition of spherical varieties, we always assume a group action G, right?
Well, we assume the action of some reductive group. So
yes.
my usual notation.
So in exercise 3, the action group is G or H.
No. The acting group. This is a good question. Yes, thank you. The acting group is this one: G cross H. Spherical for. Let me write it explicitly.
Oh, G cross H. Oh.
Yes. The acting group is G cross H. Spherical for G cross H. Exactly as in this fifth example. So in this fifth example, G itself is a spherical homogeneous space with respect to the action of G cross G. And here it is a bit more general. We consider the action of G cross H. Okay? So this property...
Exercise 2, right? In the same in exercise 2, right?
Say it again.
Well, in exercise 2, we also...
Yes, sure. The same as in exercise 2. So in exercise 2, the acting group is G, this G, and in the first case, G is this one. In the second case, G is this one. And in the third case, G is this one. Yes, you are right. So my last exercise is the following one. Does this multiplicity-free restriction property, this is a question, does this multiplicity-free restriction property hold for the following pairs of a group and a subgroup? So the group is GLN, and the subgroup is GLN minus 1. The second case is the group is SON, and the subgroup is SON minus 1. And the third case is the group G is SP to N, symplectic group, and the subgroup is SP to N minus 2, a smaller symplectic group. So the exercise is to check whether this multiplicity-free restriction property holds for these pairs of G and H, group and subgroup. Okay? So these are the exercises. Any questions so far?
Well, that exercise requires some knowledge for Lie group representation.
Well, in view of exercise 3, you have to check that the respective homogeneous spaces are spherical. And this requires, the most easy way to check sphericality is by these two properties, 2 and 3. Here you do not need any representation theory, you just have to look at the Lie algebras and so on. So if you prove exercise 3, then for exercise 4 you do not need representation theory. But of course, this is a classical thing in representation theory about these restrictions from GLN to GLN minus 1 and so on. This is classical in representation theory, and this was known before the theory of spherical homogeneous spaces and spherical varieties was constructed. But using this theory, you can check the multiplicity-free restriction property easily, I would say. Okay? Any more questions? Okay. Yes?
MFR means
multiplicity-free restriction. Multiplicity-free restriction. It is a property that if you restrict an irreducible representation from G to H, you always get a multiplicity-free representation of H. So this is multiplicity-free restriction property. Okay. Well, Now we prove that an important class of homogeneous spaces belongs to spherical homogeneous spaces. I'm not sure that we'll finish, well, I'm pretty sure that we will not be able to finish the proof today. We will finish the proof on Wednesday, on my next lecture on Wednesday, but we start with the formulation and the proof of the theorem. Let me turn to the next page. So definition. A subgroup H in my connected reductive group G is called a symmetric subgroup. Symmetric subgroup if there exists an involutive group automorphism of G, say theta, involutive and non-identical group automorphism of G, such that H almost coincides with the group of fixed points of theta. Well, almost coincides means coincides up to connected components. So let me denote it. By this circle or zero sign in the superscript. This is the notation for the identity component of H. Identity component. Identity component, which is by definition the connected component of H containing the identity element. Containing the identity element. And so a subgroup H is called symmetric if the identity components of H and the group of fixed points of some involutive automorphism of G coincide. So H coincides, let me repeat that, H coincides with the fixed point subgroup for theta up to identity component. We can reformulate this easily in terms of Lie algebras. So an equivalent formulation
well, G theta is the fixed point of theta, right? Not the
yes.
fixed group of theta.
Fixed point subgroup, fixed point subgroup. Subgroup consisting of all points fixed by theta. This is my standard notation for invariant elements. Elements which are not moved by an action of some automorphism or some group of automorphisms, doesn't matter. So equivalent formulation in terms of Lie algebras is that the Lie algebra of H coincides with the fixed point subalgebra of the Lie algebra of G under the differential of theta acting on the Lie algebra of G. By abuse of notation, I denote the differential of an automorphism by the same letter of the automorphism itself. So theta acts on the group, and its differential, denoted again by theta, acts on the Lie algebra, by the Lie algebra automorphism. But I denote it by the same letter. So on the level of Lie algebras, we do not see other connected components. We see only what happens in the neighborhood of identity. So we need not to put some subscripts like this. It is just this condition on the Lie algebras. So this is asymmetric, yes, yes. Mm-hmm.
This means that H is the eigenspace of the eigenvalue 1 of theta inside G.
Yes, yes. It's a good observation, and we'll use it in the sequel. Thank you. Yes, you are right. So this is my definition for a symmetric subgroup, and the respective homogeneous space will be called a symmetric space. So a homogeneous space Y, which is G over H, will be called a symmetric space. Okay. Probably some of you know about Riemannian symmetric spaces, which are quite popular in Riemannian geometry. And our definition is an algebraic version of this concept. Okay. Actually, some of the examples which we have seen before of homogeneous spaces, which we have seen before, are actually symmetric spaces. So let me give you a few examples. So the sphere, which we consider first, and which is a homogeneous space SON modulo SON minus 1, is symmetric. In this case, theta, well, maybe I should write it here. In this case, theta is a conjugation with the following matrix. Conjugation with the following matrix. A diagonal matrix with -1 here and unity on other diagonal entries. Conjugation with this matrix gives you the fixed point subgroup, so G theta, consisting of the matrices of the following form. Sorry, I again have chosen the wrong thickness. So G theta is consisting of the matrices of the following form. Here is the first column, here is the first row, and we have plus or -1 in here, zeros here, zeros here, and anything here. So you see that the fixed point subgroup is disconnected in this case. There are two connected components, and the identity component, when you have a +1 here, is exactly the subgroup SON minus 1, because this matrix n by n minus 1 by n minus 1 matrix here is in SON minus 1. So sphere is an example of a symmetric space. The second example is the space of quadrics, of smooth quadrics, which we have seen some time ago. It is, excuse me, it is PGLN plus 1 over PO n plus 1. In this case, the involution theta is given by the formula taking the matrix G to G inverse transpose. So the fixed point subgroup is the orthogonal group, or it's better to say the projective orthogonal group, because here we consider G as an element in PGLN plus 1. So G is considered up to a scalar multiple. So the projective orthogonal subgroup is the symmetric subgroup in PGLN plus 1. This means that the space of quadrics is a symmetric space. And the third example is G itself. Considered as a homogeneous space under G cross G, under the doubled group. Modulo the diagonal. So here, the involution theta just swaps the element in the pair G1, G2 belonging to G cross G. It just swaps the factors of the product G cross G. The fixed point subgroup is exactly the diagonal. So all these are examples of symmetric spaces, and also all these spaces are spherical. And this is not incidental. Actually, we have the following theorem. Which says that symmetric spaces are spherical. Symmetric spaces are always spherical. So we have a relatively big class of homogeneous space, of nice homogeneous space, which belong to the class of spherical homogeneous space. Okay, so let me, for the remaining.
So, Professor,
yes,
the involution theta is required to be the automorphism of an algebraic group, right?
Exactly. So, so let me maybe write down explicitly that theta is an algebraic group automorphism. Okay. So let me start the proof of the theorem. Suppose H is a symmetric subgroup in G. Then, as it was observed by one of you, the automorphism theta acts on the Lie algebra of G, or better to say its differential acts on the Lie algebra of G, and G decomposes as the direct sum of eigenspaces for this automorphism. Since the automorphism theta is an involution, the eigenspaces have eigenvalues 1 or -1. And this is this decomposition. So let me write explicitly that G plus or minus theta are theta eigenspaces of eigenvalue plus or -1 respectively. And by the way, the eigenspace of eigenvalue 1 is exactly the Lie algebra of my symmetric subgroup. And this another eigenspace is, this another eigenspace is some complementary subspace for H. Okay, so the first lemma, which I'll prove, and I think that I will stop my lecture after proving this lemma, because I will have no more time to do anything else for today. So the first lemma is the following one. So I keep my notation, which I introduced here. The lemma says that any Borel subgroup B in my reductive group G contains a theta stable maximal torus. So there exists a theta stable which is preserved by theta, not pointwise fixed, but preserved by theta. A theta stable maximal torus contained in B. Any Borel subgroup in G contains a theta stable maximal torus.
Professor, I want to ask a question.
Yes, please.
Theta stable maximal torus means maximal torus that is theta stable, or the torus that is theta stable and maximum?
It is a maximal torus among all tori in G, which is theta stable. So the first thing, maximal torus, which is theta stable. Maximal not among theta stable tori, but maximal among all tori. And at the same time, it is theta stable. Okay?
Okay.
Okay. So let me prove this lemma. We have this Borel subgroup B, and let us apply the automorphism theta to B. We get another Borel subgroup, theta of B. Okay. Consider the intersection of these two Borel subgroups. Let me denote it by R. This is B intersect with theta of B. What can we say about this subgroup? It is theta stable, obviously, because theta just interchanges, theta is an involution, it interchanges B and theta of B. So the intersection is theta stable. So this R is theta stable, and it is always solvable, connected, and contains a maximal torus of G. Well, it is a general fact from the theory of algebraic groups that the intersection of any two Borel subgroups is a connected solvable subgroup containing a maximal torus of G. I won't prove this. I will give you a reference to say to the book of Humphrey. Which I mentioned on my second lecture, linear algebraic groups. And this statement is proved in section 28.3 in a corollary to the main result of this section. So actually, this is a corollary of the Brouillard decomposition. If you know what is the Brouillard decomposition, this is a corollary of the Brouillard decomposition. So this is the references for what I just have stated.
What composition?
Brouillard decomposition. Let me write down this name.
Brouillard decomposition.
Brouillard decomposition.
Oh, Brouillard decomposition.
Yes. If you know what is it, then it follows, the statement follows from this fact. Okay, so since it is a connected, since this R is a connected solvable algebraic group, it can be decomposed as a semi-direct product of a torus, say S, and the normal unipotent subgroup, say N. So S is a torus, and N is unipotent. Okay. Now, this torus S is a maximal torus in R, and so it is a maximal torus in G, but it is not necessarily fixed by theta. So if we apply theta, we get another maximal torus in R, because R is theta stable. All maximal tori are conjugate, and this means that theta of S is conjugate to S by means of some element in N. So this element small n is in big N. Now, if you apply theta once more, you get back S. But on the other side, you get theta of N times theta of S times theta of N inverse, which is the same as theta of N times N times S times N inverse times theta of N inverse. So this element, this product, theta of N times N, normalizes the torus S. But maximal tori in connected solvable algebraic groups are self-normalizing. So this equality means that actually this element is just unity element. This product is a unity element. It is E. Or in other words, we get that theta takes N to N inverse. Okay?
Hey, Professor, so for maximal torus in a group G, the only element that normalizes S is the element in S, right?
No. For a maximal torus in G, the normalizer is bigger. The maximal torus has finite index in its normalizer, and the quotient group is what is known as the while group. But if you consider
semi-direct product, I see. In a semi-direct, no?
Yes. So the point here is that S is a maximal torus in a solvable group R, and it is known for solvable groups. Again, you may consult this book of Humphrey. For solvable groups, it is known that maximal tori in solvable groups are self-normalizing. But this element, this product, sits in N. N is also fixed by theta, because N is just the set of all unipotent elements in theta.
So does the semi-direct product decomposition apply to arbitrary Lie group?
Say it again, applied? I didn't understand.
Does the semi-direct product decomposition apply to any Lie group?
You mean, do you have a semi-direct product decomposition of a torus and something for arbitrary Lie groups?
Yes.
No, this is for solvable. This is for solvable algebraic groups.
Oh, I see.
This decomposition holds for solvable algebraic groups. Solvability is important here. Solvable connected algebraic groups. So let me finish, since I am already out of time, let me finish the proof of the lemma. So this conjugating element, n, small n, has the property that theta sends n to n inverse. And now let me remind you that there is an exponential map. There is an exponential map from the Lie algebra of n to n itself. This exponential map comes from an embedding of a unipotent group into the group of upper triangular matrices with units on the diagonal. Any unipotent group can be represented in the matrix form as a subgroup of these matrices. And its Lie algebra is represented as a Lie subalgebra in matrices which have zeros on the diagonal, triangular matrices which have zeros on the diagonal. And for these matrices, the exponential map is given just by the usual series. So exponential of xi is the unity matrix plus xi square over 2 plus etc. plus xi to the k over k factorial plus etc. And actually, this is not a series. This is a polynomial because xi is an nilpotent matrix of this form, and this series wraps at some term. So some powers starting from some k, the powers, all powers are 0. So this is a polynomial map, and it is known that this map is an isomorphism between the Lie algebra of n and n itself. So now we have this element n, which is an exponential of some xi. And since n is taken by theta to n inverse, we get that theta takes psi, the differential of theta takes psi to minus psi. Now we put n to the power 1/2 by definition to be the exponential of psi over 2. And take t to be the conjugate torus, the conjugate of s with respect to this element, n over 1/2. Then if you apply theta to t, you get theta of n over 1/2 times theta of s times theta of n over minus 1/2, the inverse element. And this is, so theta takes n over 1/2 to its inverse because of this equality, theta of psi equals minus psi. So we get theta n to the minus 1/2 here times n times s times n inverse times n over 1/2 here. And you easily see that we get just t. So this proves that the conjugate torus t is indeed theta stable, and this proves the lemma.
So how can I want
yes?
to ask a question? In the previous page, how do we deduce that theta n belongs to the group n?
So in the previous page, let me say that excuse me. Let me choose this. So let me say that n is theta stable. Theta of n is n. This is because n is just the set of all unipotent elements in R. It is stable under all automorphisms. Set of all...
the unipotent subgroup is a characteristic subgroup.
Exactly.
R, right?
You can say like this. Exactly. It is a characteristic subgroup. The maximal unipotent subgroup in a solvable Lie group is a characteristic subgroup in a solvable Lie group. It is important. The set, it is just the set of all unipotent elements. And therefore it is characteristic. Yes. So I finished the proof of the lemma, and also I finished my lecture. So if you have any more questions left, then please ask your questions. But the lecture itself is over. We shall continue the proof of the theorem on the next lecture on Wednesday.
Well, I have a question.
Yeah, please go ahead.
About the root decomposition, how can we deduce that the eigenspace is one-dimensional?
Well, I cannot explain it in few words. It comes from some representation theory of SL2. So there are some Lie subalgebras isomorphic to SL2 hidden in this picture. And if you analyze the action, the adjoint action on G, then you can prove that root subspaces are one-dimensional. I cannot explain it in one or few words. So instead, I refer you to these books by Humphrey or by Winberg and Onishik on Lie groups and algebraic groups. So this is in all textbooks, in all good textbooks on algebraic groups.
Okay, thanks for answering.
Okay. So more questions? Well, it seems that so far there are no more questions. Then let me stop sharing.
I want to answer one last question.
Yes, please.
In the root decomposition, well, the same page there, and the unipotent, the Lie algebra of the unipotent subgroup correspond to the delta plus part. Oh, I see.
Exactly. Well, at least, well, the correct formulation is that the delta plus part can be chosen in such a way that this delta plus part.
I know this is the chosen.
Yeah. Okay. So what is your question? What is your question then?
No question. I just want to assure.
Okay. So more questions? By the way, I encourage you to solve exercises. So far, we have already 5 lectures passed, and there were a number of exercises in these lectures. And I encourage you to try to solve the exercises and send me your solutions on email. So you have my email in the chat of this meeting, of this conference.
Yes.
So please send me your solutions. I will check them and respond, and we can discuss everything. And also the same concerns your questions. You are encouraged to send me your questions by email. Of course, you may ask questions at any time during the lecture, as you do. But still, between the lectures, you may write me and ask more questions. Well, more questions so far? Well, if not, then let me stop sharing the whiteboard. And I'm saying goodbye to all of you. Thank you for your attention. And hope to see you on Wednesday on my next lecture. See you. Bye-bye.